Yes, hope all of us are doing fine. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In our discussion today, I'm going to look at the concept of kinetic energy of rigid bodies, and this is going to be done in terms of an evaluation of a problem set, which I'm going to use in terms of a symbol, of course, illustration, which I've given on the right side of the board. Now, in this case, we are going to compute the kinetic energy of this specific rigid body, and of course, which is going to be forming our description for the kinetic energy for both a translation and a rotation kind of motion. Now, in this case, I've chosen this particular illustration, and if we try to look at this one, this is going to be in form of a ball, which is going to be rolling down this specific lane without slipping. So in this case, it's going to be a ball that is rolling down at the speed of 3.3 meters per second. And of course, this ball is made up of a mass of 7.3 kilograms. And of course, the distance, which is going to be given in terms of this specific aspect of 9. Just do some kind of so it's going to be having a radius of basically r given in terms of 9 centimeters given as that one. So we're going to consider this specific kind of a motion since this ball is going to be translating in this particular direction, and of course having a circular motion by rolling down, so moving in that specific motion while having a displacement towards the right side in that specific direction. So in this case, we'll compute, of course, this specific energy by considering the total kinetic energy as a sum of the kinetic energy of the translation and the rotation component. And of course, we're going to see that this is going to be given in terms of kinetic energy rotation plus kinetic energy translation given as that one. So for us, as we have been doing from our previous discussion, we have decided that basically a rigid body is going to be, so this is going to be basically a sphere. So a rigid body is going to consist of particles whereby during motion, these particles are going to maintain the same distance. And therefore, we're going to consider having its kinetic energy given as a summation of all those infinitesimal components of particles given in terms of the product of mv squared over 2 given as that one. So this is going to be giving us the concept of what we refer to as rotational energy. So therefore, from this one, we're going to consider this specific aspect whereby we're going to take into account the concept of what we refer to as angular velocity given in terms of r or omega. So in this case, we're going to use this specific description for us to find the rotational kinetic energy. So by doing a substitution, we'll have this one as a summation of m, whereby this aspect of v, the square of v is going to be, from this specific description, the square of r and omega squared given as that one. So we're going to have the whole of that one divided by 2 given as that one. So we can do a rearrangement of this specific equation to have the kinetic energy rotational component, which is going to be given in terms of the summation of mr, and then we shall have the square of that one multiplied by the square over omega r over 2 given as that one. Now, from our previous discussion, I had talked about the concept of the second moment of mass, and this one basically gave us the aspect of the moment of inertia given in terms of I. So therefore, we can describe the kinetic energy as a product of this second moment of mass together with the ratio of this specific square of omega over 2. And therefore, that's going to give us the rotational component of this specific, or rotational aspect of this specific ball, which is going to be rolling down the lane given in terms of that particular description. So as well, we can describe, so this is going to be rotational component. As well, we can describe the translation component of this specific ball by considering the kinetic energy equivalent to half mv squared. And in this case, we're going to consider this specific aspect of the total kinetic energy, then therefore equivalent to the rotational component plus the translational component. So therefore, we are going to represent them in terms of this specific aspect of the translational component, which is half mv squared, plus the rotational component, which is the moment of inertia given as that one. And of course, the square of omega over 2 given as that on the board. So in this case, this is going to be describing our total kinetic energy for this part or for this kind of a body, which we are going to consider as of course, a rigid body. And this is going to assist us evaluate, of course, what we refer to as the total kinetic energy of this specific ball. So this ball is being rolled down the lane. So therefore, in doing our substitution, we're going to find its kinetic energy given in terms of a half. Its mass is 7.3 kilograms. And then we're going to have its velocity given in terms of 3.3. So basically, I'm going to use a lower section for the sake of a space, so that we have the kinetic energy total given in terms of a half. The mass is 7.3 kilograms, and then we're going to have the velocity 3.3, and we're going to have to do a square of that one. So plus the moment of inertia in this particular case is going to be given in terms of the moment of inertia of a solid sphere. So from our previous discussion, this is going to be given in terms of 2 all over 5 m the square over r. So in this case, I'm going to do just a substitution of that one. And of course, that is going to be with the product of omega squared all over 2 given as that one. So as we can see, we can just do an evaluation of this by cancelling out the common factor. So this implies we're going to have this one as a half. So I'm just going to maintain them as numerical evaluation so that we can just do a follow-up of those one. So we shall have 3.3 square plus. So this 5 over this one, we can just do a simplification, whereby we're going to have the element of mass in this case given in terms of 7.3, and then the square of 3.3, and then we shall have this specific aspect of course, omega squared, which is going to be given in terms of v squared over r. So perhaps I'm going to maintain this one in order to avoid confusion. So in this specific case, we're going to see that we are given this aspect of omega in terms of so velocity in terms of r omega. So this implies that we can give omega in terms of v over r, and therefore the square of omega can be given in terms of v squared over r squared given as that. So in our doing our substitution for this specific case, we shall have this specific element of so we shall have this one given in terms of m r squared v squared over r to represent r squared to represent omega. So in this case, since we have a v squared from this specific section and r squared given as that one, we shall have this one substituted for the amount of so we shall have still this one I have 7.3 of course it's tedious, but it's good for us to do a follow-up. So we shall have 3.3 squared plus 1 over 5. The mass is 7.3, and then we shall have this square of radius cancelling out from this specific formula. So we're going to remain with the square of velocity, which is going to be 3.3 given as that one. So this is going to give us a kinetic energy equivalent to, so from my end, I'm going to get the value of 56 joules. So kindly confirm from the evaluation. In case we find a different figure, then we can notify so that we do appropriate correction. But we're going to do a follow-up from this one. And this specific point, we're going to utilize this particular relationship in order for us to find the final evaluation. So that's how we're going to consider the, of course, the description of kinetic energy of a rigid body, which is going to be having both rotational and translation kind of aspect given as such a ball, which we have considered in this specific equation. So that is it for now, guys. By God, please. We'll catch us in our next video.